book, they come back in your data book, there's a qualitative analysis notes, which you may have come across before, and you may have seen them in a different guise, perhaps at GCSE or what have you. But bear in mind that you have a practical exam at the end of your course, which counts for 15% of your total mark. And just under half of that, those marks, so about 6% of your total pre-U mark, goes towards qualitative analysis, or comes from qualitative analysis, i.e. putting solutions in solids and test tubes, heating them up, adding other things, and noting down your observations, and then making inferences of it from that. 6% is about the width of an M2 grade. It's about the difference between an M3 and an M1, and therefore a difference between an M2 and a D3 roughly. And of course, it would make the difference higher up. It would send you further up the rankings if you can get this right. And it's been our experience that you need a little help, I suppose, in sort of making observations and sort of working out what to do in terms of qualitative analysis. It's usually the second and or third questions on a practical paper. So you will have a titration to begin with, maybe an enthalpy change experiment, and then you'll be asked to do some qualitative analysis. So I have a whole range of chemicals here, which I'm going to go through in some order, roughly speaking in the order of the headings I've given you in this booklet, just to point out a few things to you and to show you how to do some things with which you may not be familiar. If you've got any questions, do ask. If you notice any horrendous mistakes in the booklet, then please do tell me as well, because I can alter it and send you an amendment. This will be available on Greyhound for you to download as well. So, qualitative analysis, as I said, it's putting stuff in test tubes and putting other stuff with them, or heating it or whatever, and observing your results. It's the observations that are the key to making a good qualitative analysis, or a good stab at the qualitative analysis. If you look at page, 6 or something, page 7, I've written a whole section on observations. And the first thing I've said is that all your observations should be noted down. And remember that an observation is something to do with one of your senses, your traditional senses, apart from taste, I might say. So if you see something, hear something, if you feel that it's getting hot or cold, that's an observation as well. What's the other one? Smell something, I suppose. But you need to be careful when you smell things. I'm sure you've been told before that you shouldn't directly snort in a gas that's been given off, rather than waft it in your nostrils. But all observations are valid. It may be that in the paper, not all observations will be given a mark, but you need to write everything down because you will be asked to make conclusions on things. And it's crucial, therefore, that you can make accurate observations of things. My first bullet point is talking about colour change, and I've said it's always a good idea to write down what colour it goes from and to. Quite often they're more interested in what colour it goes to, but that's not always the case. The slightly tricky things are where you get white or off-white precipitates. And I've suggested that you could use as a control a piece of paper. Because pieces of paper tend to be white. This is bad practice. Pieces of paper tend to be white, and you can sulfuric acid. The first thing. Why would you want that? Why would I want that? Thank you very much. And you can use a piece of paper as a control, or indeed try to remember what's white. So classically, we have a white solution here, a white piece of paper, white precipitate here. That's lead sulfate, and that's what you would say to be white. It doesn't really look much different from a piece of paper. There are other solutions that, when mixed together, will form off-white or slightly yellow things, slightly yellow precipitates. And it's a good idea to know what they might look like. So here I have sodium bromide and silver nitrate. Now, if you look in your qualitative analysis notes, you would see that silver nitrate with a chloride forms a white precipitate, but with a bromide, it forms what's sometimes called an off-white precipitate. And you'll see that is much yellower. Yep. Okay. Now, if you want to call that cream coloured, that's fine, but remember, that's not yellow, nor is it white. What you would class as yellow, is where you've got the iodide solution, and you get that colour there, okay? Pale yellow. Now, and compare it to the other two, you can probably, if I shake this one up a bit just to fix it, you can probably see the gradation in colour. This one is settling a bit. Hopefully you can see the difference there. Okay? And it's important that you note down the fact that it's not quite white. Now, equally, there's something to do with shade, and very specifically in your notes, very specifically, it says that when you react a chromate with lead, which I had over here somewhere, no I didn't. Lead nitrate, right. You get a bright yellow precipitate. That's what they call bright yellow. Okay, that is quite clear. It's a good idea to get used to putting things like bright or pale or whatever, because then when you're looking through your qualitative analysis notes, you can immediately key into that. Okay, and they would be looking for the word bright in this case. There is also another precipitate which is lead with iodide, forming lead iodide, which is also a pretty similar colour to that, but for some reason that's called a yellow precipitate and not a bright yellow precipitate in the QA notes. As it happens, whilst I'm on the subject, because this isn't a data book, you're not expected to learn this, but I would suggest you are quite familiar with it, in much the same way that we would hope you would be familiar with the periodic table, so you'd know your way around it. So do take time to look through this and make sure you understand the difference between adding ammonia or adding excess ammonia or adding sodium hydroxide. That will be available to you in the test. Now, many tests, however, do change. There are observations that might change over the course of a reaction. So, iron sulfate. One of the examples is where you take iron sulfate and you would add sodium hydroxide to it. And what would you get? Yep, and what does that look like? It's iron 2 sulfate. Green. Yeah, you get a dark green precipitate, okay? Sometimes called gelatinous. Now, again, in terms of shade, you would say that's dark green as opposed to the very pale yellowy green that this dilute iron sulfate solution is. But I'm going to leave that for a while and come back to it, and you'll be able to see at the top, in fact pass it round and have a look at it as it goes over time. You'll be able to see that at the top of the solution it's slowly turning brown. If you can't see that, and it has, then hello. Thank you very much. Yes, safety glasses, I should remind you about. Hopefully you can see that it's turning brown at the top of the solution. That's a telltale sign for iron 2, because what is happening to it?
Rusting.
Yes, you wouldn't put rusting on an exam paper though. It's oxidising and forming iron 3. Okay. Now, those are all standard tests, which I hope you have seen before. What you may or may not have seen before is things that happen when you heat solids. And for this purpose, you might need to get a little closer. There are all sorts of...
So you're going to show it?
Nickel sulfate.
Oh, she's doing it. She's aware.
Hello.
But is that what she's doing? Yeah.
Has it gone brown?
It certainly has.
Oh.
Can you show Julia on the camera, please?
Oh.
It's gone brown.
It's gone
It's like a scrap.
It has gone.
It hates it.
Actually.
Whole conversation. Yeah, I know.
Heating solids is where...
This is so fun.
Heating solids is where, in particular, there are always quite a lot of marks available for observations. If you turn to page 9, there are a few boxes that I've set out with some words that you may or may not understand. Has anyone here heard of the word decrepitation before? Right, okay. If you gather in closely, so you can see what's going on.
Gather in.
Gather in.
We don't know what that means. What does that mean?
Quite often when you're asked to heat a test tube, heat a solid, you'll be told to do it in a hard glass test tube. For that purpose we have small ignition tubes. They're made of Pyrex, so generally they don't crack. They might melt if you heat them strongly enough, but that's not the point. There are a number of things that you might observe when you heat this solid. This is hydrated nickel sulfate. Safe switch, please. Just watch and listen. I'm going to heat it gently to begin with, and then heat it strongly.
Pointing right at that.
If you're talking, you won't be able to hear it. Right. What did you see?
It went yellow.
Fumes coming off. It looks like gone off.
Big lumps.
Cloudy. Fumes.
Condensation.
I can't really.
Okay. Excellent. Good. Condensation. Immediately as you heat any tube, you'll probably get a little bit of condensation forming. You can see that. Okay. That's just a natural phenomenon. That's not particularly noteworthy, but you'll notice that as I carried on heating it, we have formed condensation on the inside of the tube. Okay. So that would suggest that there's water present in the crystal structure. You would observe it as condensation. What have you noticed about the colour of the substance?
Green to yellow.
It's gone from green to yellow. Did you hear anything? Yeah. Now, the word decrepitation is something that applies to when effectively crystal structures are rearranging themselves, either by giving off water or because there's a change in the crystal phase boundary. It means crackling. Okay? That's an observation.
And that's decrepitation.
That's decrepitation. Yeah.
Would it be wrong to say crackling?
You can perfectly well say crackling. Just in the same way, you can effervescence would be fizzing and bubbling if you wanted. Okay?
Fizzy bubbly.
So there are a number of things that you would have seen in this case. One is that condensation has been given off, or rather, condensation forms at the top of the ignition tube. The inference would be that water has been given off. Another is that it's changed colour. Further, that it crackled when it was heated. Some solids will do that quite quickly, some do it after a while. That's why I changed from heating it gently to heating it strongly. When you are heating something, it is always good practice to heat it gently, then strongly. It may well say so in the instructions, but sometimes you may be expected to do that yourself. There's no point nuking it straight off, because you will never see anything subtle. Likewise, you could heat a solid. It's a different solid, this is zinc oxide. And you notice there's that little bit of condensation or water vapour, just you see straight away. I've got the heat on this one. You'll see that as you heat it, again, it changes colour. Okay, can you see that it's turned yellow? Now, it sometimes pays just to be a little patient, because after a while, I let it cool, it loses that colour again. Has that gone? I can't tell. Has that gone white again?
Yeah.
White. Yep. That's called thermochromism. Okay. So there are a number of substances. Nickel sulfate, in fact, does it as well, if you don't degrade the substance too much. That's why it's in that box. But thermochromism means it changes colour with temperature. So zinc oxide, if you see a solid that goes yellow, that is white to begin with, and then it's yellow when you heat it, and then goes back to white again, most likely zinc oxide. Can you think of anything else that does that? That's the only one. As I say, long word, thermochromism. Thermochromism, it's one of the titles of the boxes.
Definitely zinc oxide.
Yeah, as far as we can tell, it's zinc oxide. You wouldn't be expected to recall that, I think. No. But bear in mind that you might come back to it and think, where is that yellow solid? Ah, well, it's there. And then finally, another solid I'm going to heat is ammonium chloride.
Sorry, so thermochromism means the solid that will go back after the cool.
It means it changes colour with temperature, essentially. So in the case of zinc oxide, it turns yellow when heated and goes back to white when it cools down again.
Could you call that physical change then? We've ended up exactly where you started.
It's a shift of electrons. Yeah.
Is it reactive?
Oh yeah, okay. No, true, good point. It's not reactive as much, because you've still got zinc oxide, either end of the temperature scale. This is ammonium chloride, and when you heat this, hoping that you've got to be careful with this, because it's not the longest tube in the world.
Good luck, sir.
Shortest tube.
Oh, no, that's okay. What do you notice here?
What is it? It's kind of
So as I've heated it, that's
progressing up the tube. Turning to gas. What is it?
So what would you say has happened there?
Sublime.
Yeah, your inference is that it's sublimed and then deposited itself. So in terms of an observation, you would see a white solid being formed on the walls of, or eventually near the mouth of the tube. Okay? And that's your sublimation and reverse sublimation or deposition or whatever you want to call it process. You can check that that's what's happening by just moving the flame slightly up, and you'll see that as the entire test tube heats up, the solid keeps moving. Now, in terms of, I heard when I was talking about the hydrated nickel sulfate, I heard someone say that it was smoking. That's not a funny term. I have noted that there is a difference between smoking, smoke, and a vapour. And in the case of the hydrated salt, it's most likely to be a vapour. Okay, it's quite tricky to tell, but of course, a smoke is a suspension of solid particles in air or in a gas, whereas a vapour is liquid particles suspended in the vapour. In the gas. I'm not really sure of any way I can best tell you how to look out for that, other than just think, well, is that a solid or a liquid? Careful observation. Yeah.
Is it when you get a vapour, or is it when you get a vapour you say it's effervescent?
No, I'm talking about something else. So effervescence is where you've got is a solution, and there's a gas being evolved from a chemical reaction within the solution. Okay, so the effervescence, you would say, is the fizzing and the bubbling down in the.
Oh, so it's not actually gas.
No, that's just gas. So vapour, what I'm thinking of particularly is if sometimes you might see HCl gas reacting with water vapour, and you get misty fumes. There's a standard phrase for that, and that's a liquid. Whereas that there is a solid. Formation of precipitates. Now, I said you need. I said you need to be fairly familiar with the qualitative analysis notes, and the reason for that is because there are some quite subtle differences between some ions. And in fact, if you look at when you look at these notes, you'll see that there are some ions that behave exactly the same, depending no matter whether you add ammonia or sodium hydroxide to them. And I've picked out two examples. One is where you've got something with lead cations in it, and one is one where you've got, hopefully, magnesium sulfate. Is there magnesium sulfate over there?
Yeah.
Just while we're waiting, small note. When it says add a 1 centimetre depth, that's what it means. It doesn't, or add 1 cubic centimetre. It doesn't mean exactly measure it out. We're not looking to be utterly accurate on these things. Thank you very much. You know how to judge half a centimetre. What it doesn't mean is add in 3 or 1.5 inches, 2 inches worth. That is half a centimetre. If you're in any doubt, the depth of your little finger is roughly 1 centimetre. It doesn't matter how. Yes, it doesn't matter how fat fingers you've got. That's roughly 1 centimetre. Okay.
Yeah, I told you that last time.
So quite often they'll ask you to put 1 centimetre depth in, and then another centimetre's depth of another solution out, or just add a few drops. And in this case here, if you wouldn't mind paying attention, lovely. In this case, I've just added a few drops of sodium hydroxide to lead nitrate solution and formed this lead hydroxide. Now, if I keep adding sodium hydroxide to it, there we go, I didn't need to add very much, you'll notice that the precipitate dissolves again. Okay? That's what it means when you add excess. Okay? It's expecting you to say if there is any further change, i.e. the precipitate might redissolve or not. Compare that with magnesium sulfate. So another centimetre's depth worth there, and add sodium hydroxide, and you get a precipitate that looks rather different, because it's really not quite as obvious, much fainter. But if I add more sodium hydroxide to it, you never get back. I'll do it once more just to prove it. You never get back to your absolutely clear solution. Yeah? There's still that faint precipitate. And this is something you do be careful of. I lose track of the number of times people say, has that redissolved? Does it look like water? Would you drink water like that? If it doesn't, then there's something there in the way, and that's not fully clear. Okay? Does that make sense?
Should you do that with every precipitate you get?
Yes. Yeah. There are a number of different types of instructions. Sometimes it will say just add a few drops or whatever. But if it asks you just to add sodium hydroxide, you have to take it for granted that you will add a little and then to excess. Okay. Now, when it comes to heating solutions,
Can I just say something?
yeah, go on.
When you're doing that, the two solutions you want to be very aware of, where you want to add a few drops then an excess, are sodium hydroxide and also ammonia.
Oh yes, thank you.
They're the two where you are liable to get something redissolving. However, you should, as a matter of course, add a bit of excess for everything, but the alarm bell should be ringing if it's ammonia or sodium hydroxide. And the cation tests are sodium hydroxide and ammonia. So
That's the metal ones.
Thank you very much.
The metal
Now, you've seen me heat solids,
Right,
and we
time.
used little hard glass test tubes for that.
Thomas.
And you've seen me do a number of reactions in normal test tubes. It always says quite specifically, if you are heating solutions, you must do it in a boiling tube. This is a boiling tube, yeah, in case you're in any doubt. It's got a wider diameter, so that means it takes more liquid. So do be careful of that. I'm going to show you two specific tests that involve heating solutions, and the first of these is heating ammonium chloride solution. Is there ammonium chloride solution anywhere? If not, I'll make it up. No. Well, I can make up the solution.
Oh, you've got the solid.
Yeah.
5, 4, 3, 2, 1.